So I'm Schuyler St. and today I'm going to be talking about SDR, or software-defined radio. So just to get a view of the audience, how many of you have heard of software-defined radio? Okay, how many of you have actually used a software-defined radio? Okay, how many of you think that radio is the thing that you want to be doing? Okay, how many of you know physics then? Okay, there's not exactly the best overlap is radio. You need to know a lot of physics, especially for higher frequency stuff. But anyways, so software-defined radio, essentially it is, instead of having software to demodulate and receive your signal, you're going to use instead of having hardware that demodulates the signal, use software to do it. So what this means is that you can receive many more signals with a single piece of hardware, but you still need hardware to receive the signal. So what a typical radio receiver looks like, and this is one, but you have other things, is you'll have an antenna here. That's what the triangle thingy here is. You'll then have, this is LNA stands for low noise amplifier, and BPF stands for bandpass filter. So this amplifies and filters the signal. You then have this thing here called a mixer, and a mixer does stuff. It essentially multiplies two signals together. This signal is a signal you generate. This signal is the stuff from the antenna. And with a mixer, there's a trigonometric math thing that explains how it works that I don't understand because it's big, crazy, long math thing. But essentially what this does is it takes a frequency that's a radio frequency. In this case, this would be like a FM radio. So it'd receive like something at 100.5 megahertz, and it will shift it down to either start at be at 0 hertz or be at some intermediate frequency. Then you see IF here, because that's the intermediate frequency. Here's more filtering, amplifier filtering, then a limiter, which just makes sure the signal is in a correct amplitude. And then it demodulates it, and here this would go to your speaker. Software-defined radio, you're going to have something similar. You have an antenna, but then you have RF hardware. So this will still have a mixer. It might have some filters to help you get the signal you want to better. But then it just goes into an ADC, and then you'd have a DAC, or digital to analog converter, to transmit. And the reason that you have that it just goes straight into the ADC is this way there's no processing of the data in hardware other than shifting the frequency down to be sampled by the ADC. So now your computer can do all the work. And then here, the digital front end here, this will just take samples from the ADC, put them in a format your computer can understand either with USB or Ethernet. And then processing, so on some devices like this Blade RF I have here, it has an FPGA on it, and you can use the FPGA to do programming. Have any of you heard of an FPGA? Okay, so an FPGA, it's a device that you can use software to make hardware with. It stands for Field Programmable Gate Array. Essentially what it means is you write a program that represents more hardware than software, and when you program it, it will reconfigure logic elements to do it. So it's typically you'll see this for high-speed things, or you'll use it to do typically high-speed things because it's more hardware, but also if you're doing lots of complex signal processing, you can do it in them. But then eventually it goes to your computer. Now, one of the things with software-defined radio is if you're operating at a higher sample rate, so your ADC and if you can transmit your DAC is running faster, then you're going to get into, well, you're going to need a more powerful computer to handle all of those samples. So as far as available hardware, you start out at pretty cheap, the Realtek SDR dongle, this dongle here. This originally was designed as a TV tuner in Europe. You can't use it as a TV tuner in the US because it doesn't have enough bandwidth. So I'll pass this around and people can look at this. So bandwidth is how much of the spectrum that you can look at once. Are all of you familiar with bandwidth and frequency and all that? Is anyone not familiar with it? Okay, so essentially right now, like this dongle, depending on the exact hardware in it, so who makes it, you'll have a range of about 24 to 17,000 megahertz or 1.7 gigahertz. Some of them only go from about 50 to 1,000 megahertz. It depends on the model you get. Then there's the FunCube Dongle Pro Plus. This has a wider frequency range, and what's cool about this is it was actually designed to be used with the FunCube satellite. So you plug it in your computer, connect it to an antenna, and you can use it to receive signals from the satellite. Well, with this, you can also receive RF signals too. Now, the top two dongles here, these are receive only, so you can't transmit anything. All these other devices here, you can transmit with. So, have any of you heard of the Hack RF? Okay, so the Hack RF, it's a software-defined radio transceiver. It can both transmit and receive. But the problem with this, but the one thing you have to be careful with it is you can only do one at a time. So you can either transmit or you can receive, but you can't do both. And this has a really wide frequency bandwidth though. So from 10 megahertz. So this is well below the FM broadcast band up to 6 gigahertz. So with this, you can look at signals from, say, 5 gigahertz Wi-Fi and higher frequency stuff around there. And if you get what's called other mixers and stuff, you can look at higher or lower frequencies with any of these. This is the Blade RF here, and this is what I'm going to be using for this along with the RTL SDR. And the Blade RF is what's called full duplex, so it can transmit and receive at the same time. So this is useful. There's actually software you can use this to make a cellular base station. The important thing though is you need to make sure that you're licensed, because if you aren't licensed, you will get in trouble with the FCC, and that means that people aren't happy. So, and then there's also, for more expensive things, you'll see there's a lot of the USRP series things. These are all made by Edis Research. And the USRP-1, the reason I don't have a frequency range here is you buy the board, but then you have to get a daughter board to plug into it for depending on what type of signals you want to receive. The B200 and the B210, what's interesting about these is these are pretty much the same, except the FPGA on them is different. The B210 has a FPGA that can hold more hardware or more logic elements, and you can make it do more complex things. And then the UMTRX is really interesting. It's essentially two of those Blade RFs connected together. So it has two of the transceiver parts instead of one. And it uses Ethernet instead of USB 3. And then there's the Matchstick, which they don't say the IC they use for the RF transmitting and receiving. But if you notice, it has the same frequency range as the UMTRX and the Blade RF, so I do believe it uses the same part. And it also has a 12-bit ADC and 40 megahertz bandwidth, so it seems like it's very, very similar. What's cool about the Matchstick though is it's really tiny. It appears to be about this big, except it's really expensive. But it essentially is a Linux mini computer with software-defined radio. So of course, there's hardware and we need software. So, have any of you heard of GNU Radio? Okay, so GNU Radio, it's primarily for SDR and software-defined radio, but you can use it for other digital signal processing, but this is really what it's designed for. So, it includes GNU Radio Companion. Have you heard of that? So, GNU Radio Companion, it's this really cool tool, and it's essentially a code generator for Python. So, you'll have these blocks, and you'll put blocks down and you'll connect them together. So to make something that will say demodulate an FM signal, you will connect the source from your radio to a filter and converter to a demodulator to an audio sync, which will then play it on your speakers. There's GR-Osmo SDR. Now this is like all-in-one drivers for most of the hardware that I mentioned. So typically the way you'll see the software set up is you'll see that you'll need to get the library for your specific device, but there's also the GR-Osmo SDR library that provides you with one block instead of 20 different ones for each different device you want to use. And this one block, you just tell it, I want to use Blade RF or Hack RF or RTL SDR or FunCube dongle. And then if you want to look at the spectrum without having to make fancy signal processing stuff, you can use this software here. So Linrad is a software you can use for viewing spectrums. It originally stood for Linux radio, but you can run it on Mac and Windows too. For Windows, you have SDR Sharp and HDSDR. Both of these are closed source. For this, I'm going to be using GQRX though. So GQRX, I don't believe it stands for anything, but it might. And this is a spectrum viewer. It's open source and it uses Qt for the graphics, and I'm going to be using it for everything today. And then for software, you can also run this on Android. So this is currently, you can use the RTL SDR, and I just found this out last night. Someone took the Hack RF library, so that's a different software-defined radio, and they ported it to Android. So you can't do all the same things as these apps, but you can record data, then play it back. So SDR Touch and RTL 2832U driver, those you can use to just view the spectrum. And then ADSB receiver and ADSB on USB RTL, those apps can be used for receiving and looking at ADSB data, which is broadcast from a plane saying, hey, I'm here, I'm moving this fast, I'm at this altitude, and so forth. And to connect the SDR device to your Android phone, you're going to need what's called a USB on-the-go adapter. So you'll see micro USB on one side and a regular USB-A where you can plug something into on the other side. So now we're going to look at the spectrum, and we're going to also receive some broadcasts. If we have time, we'll do some other things. I took some screenshots because I don't have a microwave here to show you everything that I have at home. But so here's the FM broadcast band. And for this, I'm using the GR-Osmo SDR library. And there's a built-in tool called Phosphor, which you need a separate library to do part of it, but it's really cool. It gives you this, it uses your GPU to compute the frequency spectrum instead of your CPU. So this moves really quickly, and it's really cool because you can see signals much more quickly than if your CPU computes it. So does anyone recognize what these signals are?
Looks like a spectrum.
Yeah, so this is the FM broadcast band, and if you look here, here's 91.5, and then here's 92.3. So here's the frequency in megahertz, and if you'll see, there's this inner area here that is where the voice is modulated. Are all of you familiar with how FM works? Is anyone not familiar? Okay, if you have any questions about this, just raise your hand and interrupt me and I'll answer them. But if you notice on the sides here, you see these big bands. Now these bands here aren't part of the voice data that you normally get. What this is the RDS or radio data system data here. What's cool is the way the standard's designed is your analog receiver, or if you have an older receiver that doesn't have the standard built in, your analog receiver will look at here, and as you tune across, this looks like noise, but it's actually data. But the way they encode it, it looks like noise. So as you tune across, if you have a knob you can turn and it will still play sound. A lot of the newer ones will only go to frequencies that have a station there. But if you do it, you'll just hear static. But when you tune it here, you'll get the data. And it's only looking at this much spectrum. And then same for this radio station here. So RDS is how your station will say, I'm this name, I'm playing this song, whatever. Yeah. So this is a look at Wi-Fi, and this is where, and for this I'm using the Blade RF instead of the RTL SDR dongle. And if you notice, this is actually a very wide spectrum. You can't really see it. The image is sort of shrunk down too much. But this is about 24 24,000 or 2,412 megahertz or 2.412 gigahertz. And this goes up to about 2,452 megahertz. So this is 40 megahertz of bandwidth, and that you can get with the Blade RF because the Blade RF has an ADC that will sample at about 40 megasamples per second. So this is in the 2.4 gigahertz spectrum. This is centered around 2.437 megahertz. And does anyone know what channel this is?
That's what the internet's for. Look it up.
Yeah, I know. It's this is channel 6 actually, and this is my home Wi-Fi network. And the reason you see all this bursty stuff here is I just went on YouTube and opened some video thing. So it's going to download everything, and that's a lot of data. So you'll see a lot of packets. And this is where phosphor is really useful, because this is pretty fast. This is maybe only a second of time. So you can see this go by, and you can see there's a slight pause in getting the data here. So then this here is a microwave, like your microwave oven. And your microwave, this is actually really interesting. So you know how the door, there's the metal grid, and it's all metal on the inside? So that's what's called a Faraday cage, and that's designed to block radio waves from getting in there. Well, your microwave, if you see like it says 1,000 watts or 500 watts, depending on how they brand it, if you look at the FCC reports, it may be slightly less. I looked, and sometimes the actual power is a little lower than what they brand it as. But it's putting that much power in there to heat your food. But those radio waves leak out. So this is in another room over, probably about 30 or 40 feet away from the microwave, and you can see I'm getting a lot of signal here. And all this is because the microwave, if you really want to shield it well, it costs money to have a lot of metal. So they do good enough, and the FCC says it's good enough. One other thing you'll notice here is there's this constant peak here. This peak isn't actually in the spectrum. This peak is what's called a DC offset, and it has to do with the way you sample the data when you shift the frequency down from, in this case, 2.45 gigahertz to around essentially 0 hertz, you're going to get some DC offset stuff, so you'll get this peak in the middle. You can get past this by either, if you have a narrower band signal you're looking at, tune off to the side, or you can just ignore it. There are some things you can do in the radio's hardware configuration to actually get that peak to go away, but unless you need the entire bandwidth and this peak is going to horribly mess things up, it's probably okay. There are certain radio designs where instead of bringing the frequency down from, so what you essentially do is, if here's your frequency and here's your amplitude, if your signal's up here and there's a peak here, it'll go through the mixer, so this thing, and your signal will go in, and then you'll have a local oscillator. And what you'll do is, the signal out here will have a peak somewhere, typically it will be centered around, or be around 0 hertz. There's what's called low IF, or low intermediate frequency, and that's the frequency here. And that means they'll put it up at around maybe 10 to 100 kilohertz. When you do that, you typically get rid of the DC offset. But it also means your ADC needs to be faster. So it's really just a trade-off of what do you want. But yeah. And then, do all of you know that microwaves and Wi-Fi routers don't mix well? Okay, good. So this is actually a screenshot of the microwave here. So you can see the microwave is running. But this is also Wi-Fi data here. So this is that same channel, channel 6. This is a 2.438 gigahertz. And then here's the microwave. So you can see the microwave transmits these bursts of stuff. And this is, again, I'm pretty close to the router, so the signal looks stronger. But if your router is next to the microwave, you'll get a few issues. So first of all, if we go back to our spectrum here, so if you have your Wi-Fi thing, and the way Wi-Fi works is you're familiar with channel widths of 20 megahertz or 40 megahertz, right? So this width from about here to here is about 20 megahertz. And so if we go over here, you'll see, so if we have our channel here that we're using, and let's say there's a faraway client, so this signal is, and here's the noise. So the signals, you can discern it, but you don't have that great strength. So your Wi-Fi router might turn up the gain internally so the signal gets boosted. The problem is that when your microwave comes along, it will raise the noise more, but it might also just blast over the weaker signal. But let's say it goes up here and puts out stuff and it doesn't go over your Wi-Fi signal. What can happen is, depending on the architecture of your Wi-Fi card, and this is actually a big problem for cell towers, is that if you have a close client and a far client, or in this case you have microwave generating noise, this will cause issues with the amplifier, and it might peak or clip, or it could damage the ADC if the voltage gets too high. So this can be another problem where your router needs to turn down the gain, but then it can't receive the signal. So now we're going to do some actual demos. Can I have these? So first we'll look at the FM broadcast band, and we'll actually receive some signals. So what we'll do here is I'm going to mirror my screens. So if we look here, we'll see disarrangement, mirror. Can all of you see this well? So I'm using GQRX for this. Currently, I'm building it from source. It's really easy to do. If you're installing a new radio, building it from source is a pain. If you have a package manager do it, it's nicer. It still takes sort of a while. So on a Mac, to open the GQRX application, so first I'll go to it, and then the build directory. So I already have built it, but you'll see there's this folder. This is actually a folder, gqrx.app. You have to do open gqrx.app, and open will take care of getting the executable running correctly. So if we load this, so first so here in GQRX we can set up our radio, so Realtek dongle, and then we'll say 2,000 or 2 million hertz or 2 million samples per second. So what this means is a sample in this case is a pair of I and Q values that's doing complex number sampling. How many of you are familiar with complex numbers? How many of you remember learning about them in school? Okay, so they aren't that complex, but essentially it's two numbers and you do stuff. I'll show a visualization later, but right now it works. So if we tune to the FM broadcast band, and that's around, say, 95 megahertz, and we start, we'll see here that we see a peak here and a peak here. These peaks here, does anyone know what these peaks are from? So these peaks are not part of the broadcast band. These are what's called spurious emissions. And this means that there's something here putting these off. Like if you saw in the diagram I showed in my presentation, you don't see those. That's because at my house I don't have that. So one thing might be this monitor. So if we turn it off, we don't see they go away, and you can try all sorts of things. One interesting thing though is that if you look at, say, I have an HDMI cable going from my computer to my monitor, and I noticed that I saw a bunch of these peaks around, I think it was about 450-ish megahertz. And if you disable the HDMI interface, or my computer went to sleep and it stopped sending data, those peaks would go away. So one interesting thing is, you've all heard about, do you have a question?
I was just wondering what the interval was of those spikes.
Of these spikes?
Yeah, and it looks like heterodyning.
Yeah.
Like you actually have your LOs leaking.
Well, it wasn't doing it at my house with this same thing, yeah.
It's probably birdies from something in the room.
Yeah, 94.63 megahertz to 94.7, so about 0.7 megahertz.
Switching power supply can do that across a wide.
Yeah, well, right now I'm battery powered. Then again, it could be ground looping. RF is weird. So anyways, what can happen is, if, like, CRT's had this issue, and there's actually, I don't remember the program's name, but if you heard of the program that'll display fancy image, like, stuff on your computer screen or your CRT screen, you tune an AM radio to the right frequency and you'll hear music. Do any of you remember that? No, it's an old one. So with your computer screen, it's emitting stuff, and you could probably receive data from it if you did fancy math stuff. So right now we're just going to use we're just going to look at the FM data. So I'm going to turn up the volume here. Actually, the projector should have sound. So here we can see, so in GQRX, I'm going to turn this off. So in GQRX, here we can turn up the gain for the dongle here. You'll have different sliders depending on what your hardware has. This has 3 different amplifiers you can configure. This only has 1, so if I turn the gain back up a little. So we can go through this frequency. Over here we can set how it demodulates it, so how wide of a section to demodulate and what to demodulate it with: wideband FM, narrowband FM, stereo or mono, AM, lower side band. So you have the peak at you have the center frequency. Is it on the lower half, the upper half, or continuous wave, lower and upper? I don't entirely understand the difference between continuous wave and upper and lower sideband. I think one's FM and one's AM. I don't use them mostly. So another thing is, if we go over here and we turn up the gain, we should be able to see the peaks. Let's see, is there a better station? Here. So at this station here, at around 100 point, this would be 100.7 FM. So if we look here, we can see these 2 peaks here, or like blocks here. These are the RDS, or radio data system sideband, and we can actually decode that and see what the station's saying. Another thing is, are you familiar with those traffic receiver things that will say the current traffic is whatever and they don't cost anything, or it's for life? Some of those actually use the data encoded with the radio data system to get that, because some stations will encode traffic information. So you open up a terminal, we'll just start GNU Radio, and that's GNU Radio Companion, and it will open. You need Xquartz installed if you're doing it on a Mac, and GNU Radios should open. Actually, I do need to close GQRX so I can get access to the dongle. GQRX, when you click stop running the DSP, it doesn't completely close out the device. So if you try and open that device with some other program, it will have an error. So this is a block diagram I found online for demodulating the FM and also showing you the RDS stuff. Essentially what happens is, here's your source, so data coming from the antenna in the dongle. This is a filter that, in this case, might be doing some frequency translating. Here they're demodulating the FM signal, and you see audio decimation for, no, that's not as cool as it sounds. It's really just dividing the samples so they're 4 times slower. So it goes from 1 megasample per second to 250 kilosamples per second. Also notice here these are blue, here this is orange. The blue up here means that it's a complex signal pair. This means that it's I think it's a float. Let's say, no, let's look at this one then. It's a float. So this is just a float, but it's only the real value because this is audio data, so it's not complex. So if we run this flow chart, it will load event quick soon, but one of the important things to know is with software-defined radio, because you have a lot of data, so this dongle here is doing about 1 megasamples per second. Each sample is 2 8-bit values, so it's doing 16 million bits per second. And then your computer needs to be able to process it. Your USB interface needs to if you have 20 of these plugged into the same USB controller, it probably won't work well, because each of those are saying, essentially goes through a hub like, I need to send data, and I need to send data, and eventually there's no more room. The Blade RF, to get full 40 megasamples per second and not drop packets, what you need to do is you need to use USB 3. My Mac only has USB 2, so you can do 40 megasamples per second, but you will lose packets because it's more bandwidth than USB 2 can handle. So if we turn this up, right now you'll hear static, but if we go to 96.9, we should get something. If we turn up the gain here, so we can get we hear the song, but also we see it's decoding down here, and here you're seeing the blocks of data. So up here, you can select to view different things. So the demodulated FM, the left and right, and the left minus right. So the way FM gives you stereo, it's really cool. It broadcasts the left plus right and the left minus right. And you do math to figure out what the FM should, or the stereo should be in your receiver. But if we look over here at RDS constellation, are you familiar with what a constellation plot is? So the constellation plot is depending on your signaling method. So let's say we send signals using frequency shift keying. So we'll have, or amplitude frequency shift keying. So we're using amplitude and frequency. In this axis we can have amplitude. In this axis we'll have frequency. So what we'll do is we'll say when the frequency is so much and the amplitude 0, we'll put it here. And then when it's this is another data. So maybe this is a 1, and this is a 0. So in a constellation plot, you want separation between your data points here. So if you have a lot of bad signal and your points for 1s are received as like this, and your 0s are received like this, you really have no separation here. So this could be either a 1 or a 0 here. So in this case, the constellation plot isn't too good. You can see there's supposed to be 2 things here. If we 100.1 should work. So we can turn up the gain. Let's try 100. And also this is where my house isn't near here, so you're going to get different stuff. So this is deciding that it's not going to receive well. So you can hear it. This is NPR. It should. The problem is right now the signal's not that great for whatever reason. So we could go through 90. We can go through. So actually what we can do is we can stop this, open GQRX, and we can look through for a spectrum that has nice, well-defined peaks. So what we want to do is, let's say 101.5 looks good. So we'll run this. You need to kill them every time, or else it will try and use the same device that isn't there, 101.5. We'll turn up the RF gain all the way. So now, okay, so now it's receiving it. We look at our constellation. You'll see there's better separation. Our house is near South Mountain, so that's probably why I get nice. You'll have a cluster of points here and a cluster of points here. But if you notice, it is decoding this. So the station is Calvin something, and the text they're sending is now playing Summer by Calvin Harris. There's other data like TP and TA says it's a traffic program, so they transmit traffic data, and TA is it's actually sending it. SPTY, it's like some other data sending thing, and you all see traffic through that. But yeah, so there's that. If we want to look at, say, Wi-Fi or other stuff, we can do that with the Blade RF, which I'm going to connect up now. So for this, I'm going to use Phosphor, which is that thing that I talked about earlier, and that will give you a really cool look at it. So we can just do Osmocom, FFT, TAC, capital F. Actually, I need a device connected for it. Hold on. So what you need to do is, if you have multiple devices connected, what you need to do is you'll do -A for this, and then you'll do, in quotes, say Blade RF equals 0, or RTL equals 0, or Blade RF equals 1. Question?
Yeah, so what was the software program that you did the IQ plot?
So this isn't an IQ.
We were just running the IQ plot. What was that program called?
This, you mean this here? So this actually isn't an IQ plot, I'm pretty sure. I'm not sure what they're plotting. It's just different data things. But what this is in GNU Radio Companion. Look up GR-RDS. It stands for GNU Radio-Radio Data System. And that's what this software is. I got it from GitHub. It's in the end of my slides. But yeah. So anyways, if I connect up the Blade RF, because it uses an FPGA, how many of you here have actually used an FPGA? So you know how most of them you need a separate flash to store the data in? So what the Blade RF does is you're connecting it to a computer. So what they do is, instead of having a flash on here, you load the FPGA image when you connect it to your computer. You can set it up where it's stored in the flash for the firmware and the processor on here. There's an ARM Here, let me see if this will work. There's an ARM processor on the FPG, on the Blade RF, and you could get that to do the same thing. Power on, no. Okay, on. So if we look at the Blade RF, should see something. Turning on, turning on. Okay, and maybe, okay, so light, let's see, just, where's light? Is there a light? Lamp. So if we look at it, I have a case on it, so you can't really see it the best, but here's the FPGA, here's the ARM processor, and then under this can here is the Lime Microsystems LMS 6000 2D, and that's essentially an all-in-one RF transceiver. It does the receiving, the transmitting, the mixing, and has the ADCs in it. So with the Blade RF, it only goes down to about 300 megahertz, which isn't low enough to go to the FM broadcast band. You can get a transverter board that plugs on top of this and has more mixers to downshift it. Now, there are also these headers here, and these headers here let you go past the mixer and connect to what's called the baseband. And what that means is you connect to essentially right before the ADCs. So if you want to do really low frequency stuff, you could tell it use the baseband and sample from there, but I haven't done that yet. So I'm going to switch back to my laptop. And if I connect the Blade RF and we do Osmocom FFT-F, we could do -A, Blade RF equals 0. This will run. Also, this dongle, depending on version you get, this is wider than the spacing between USB ports on a Mac. So it's really annoying if you want to have two devices in with two USB ports right next to each other. Get a USB extension cable and make sure it works. I have found some cheap ones that don't actually work entirely, but you can plug into the extension cable, plug the cable into your computer and do that, and that will work too. One other thing, this cable acts as a giant antenna, so this will radiate more noise. But for this, I'm not doing fancy RF measurement, so it doesn't matter. So here's the Osmocom FFT Spectrum browser with phosphor. So if you press Q, you can move the separation. Arrow keys will change the gain and the position of so this signal's in decibels. Are all of you familiar with decibels? Yeah, so it uses, do you have a question? Oh, okay. So decibels, it's fancy math. Mike Osmond, he has a series on SDR. He has a nice thing about decibels and stuff, and he has a brother that's about 10 feet tall. He's referring to his brother relative to his height. So if we look at 2.4 gigahertz, and I'll turn down the gain here. So at 2.4 gigahertz, we won't see anything. So these are, you see more, we have more gain controls here, LNA gain, VGA1, and VGA2. So this is low noise amplifier and variable gain amplifier. I'll tell you the block diagram for the part later, but essentially if we go to 2.4, let's look at 2.437 gigahertz. Wait, is this running? Oh no, this is using the, sample rate. So it defaults to 160 kilosamples per second. So it's really low frequency or slow sample rate. I'll just do 40 megasamples per second, and now we're seeing stuff. So if we tune up a little to say 2.45 gigahertz, we see this, and it goes from about 2.454 to 2.46 or ish. So that's probably a Wi-Fi thing. And also you can see with the 2.45, if we look here, we can see there's so here's the DC offset. This is running really fast, which is cool, so you can see all this stuff. And are any of you familiar with a real-time spectrum analyzer? Okay, a few of you. So it's a really cool thing. It's sort of like this, essentially, where you compute the FFTs, which it gets you this frequency versus amplitude really, really, really quickly. And then you do color gradients for what happens a lot. So if we look here, we can see there's a signal here, but it's pretty brief. And then here we can see noise. We can also look at, another thing is I'm wearing a wireless mic for the camera. You can tune into those. So if we go to This is on 626.3 megahertz. Yeah?
Can you program your radios, anyone that you can think of,
Yeah.
to be a swept spectrum analyzer? What if I wanted to sit in my home and I shut everything off, and then I wanted to program just a sweep with a certain sensitivity, so sweep within 500 yards, give me all the radio sources.
So you can't really determine distance well. What you can do is you can say the amplitude of the signal, if it's above or below. I know someone, I believe, wrote a program for it. I'm not sure if it's available. It wouldn't be too hard. You'd probably just use GNU Radio, and you'd have to write something yourself or mash other stuff together. But essentially you'd say, go through the frequency, like look at this bandwidth for say 10 seconds, compute the FFTs. If the signal that's above say negative 50 decibels, print out that frequency, and then you could go look back at it later.
It's like study at home.
Yeah. Yeah. So right now you're seeing, so here's my voice, and as I talk you'll see it, this is FM. We can actually receive this. So if we go back to GQRX here, so if we do open GQRX. GQRX is nice because you don't need to do anything with flow graph, and in this case I'm using the RTL SDR because 626 megahertz is within its frequency range. It's the wrong one. We do start, then we do 626.3. And we should, hold on. And we hear me, sort of. Yeah, so you can hear me. If you notice, there's a delay. And, did you have a question?
I just said digital echo.
Oh yeah. The delay there that you're getting is from signal process. There's some delay because to process all the signals, it's slowly taking a little longer probably. And eventually if you left this running for 2 days or something, you can see there's a longer delay. But you can receive signals. So one of the more nefarious uses for this is there's a conference that you aren't invited to or you're of someone who you don't necessarily like. You go outside in the plumber's van. Don't use a pizza delivery truck because if a pizza delivery truck is there for a long time, it's suspicious because they deliver, not stay. But if you get some directional antennas, some nice amplifiers, and this is where the Blade RF really shines, because if I change this to use the Blade RF, and we do 40 megasamples per second, 40, 1, 2, 3, 4, 5, 6.
One conference, you can find equipment.
So if we do 40 megasamples per second, what we're doing here is, I'm just going to stop the demodulation so it uses less CPU. For this, it's using the GPU, but right now we're looking at from about 608 to 643 megahertz. The transmitters come in frequency banks, and this has a frequency range of about 45 megahertz, and I think there are about 3 or 4 of them. So with about 3 or 4 of these, you could receive most stuff, and also you can transmit. So have any of you heard of DEF CON? So it's a computer security conference. If you notice, they use wired mics, and this is why. It's not so much to keep you from eavesdropping in, I believe, it's more to say so you don't go there with one of these nice directional antenna, an amplifier, and start playing music over them or whatever. But yeah, so there's a lot of stuff you can do. Have any of you heard of Radio Reference? So Radio Reference is a website where, hold on, radioreference.com. You can put in your area, so if we go to databases, okay, great. I'm pretty sure I do have Flash. But anyways, if we go to the Phoenix metro area, or yeah, sure. Then you go to, like, say, yeah, I want to find stuff for Maricopa County. We can look at all the frequencies here. Apparently they thinks I don't have Flash. I do have Flash, but so you can say that emergency management's on 47 megahertz. In Avondale at 460 megahertz. We see these things. We can look through, so you could tune to these frequencies. So this is what, like, your police scanner would look at, say, all these frequencies, fire department, Valley Metro, so this is public transit. And then this is all commercial business stuff. Another thing that there also is that you aren't allowed to listen to because of FCC rules is pagers. So pagers are still in use a lot. They're used a lot by medical personnel, and it's really interesting. These are really high power transmitters, and you can go online and find videos of people doing this, but don't do this, it's legal. And there is software to demodulate the pager signals, and there's alphanumeric pagers. So you can, and you'll see, like, someone else gave a talk about looking through all sorts of RF stuff, and they said they saw a page saying username and password, or someone saying want to go get some coffee to someone. And this is all unencrypted, so you could send fake pages, you can know what the pagers are doing, so there's a lot of stuff you can do here. Now, but
the encrypted, can you put a decrypt module, or can you put a...
Yeah, so there are different types of encryption systems. Like, have any of you heard of Project 25, P25?
Code P25 you're talking about?
So I think.
The fire department.
Yeah, the federal standard for all radios that work together. So with that, if you go to the Osmocom website, Osmocom has a lot of cool projects, actually. So there's the OP25 one, which is like Open Project 25 or something. And what this is you can receive it, decode it, you can do all sorts of things. The way Motorola has implemented P25, there are some security flaws where, like, they can sometimes transmit the key in plain text and stuff. But there's certain things, like some of this stuff, you can do it, but you aren't actually doing it because FCC says it's illegal. I really would like the FCC, because the problem with pagers is the FCC, I believe there's something like they can't be encrypted, but you can't listen to them, and that's not really a solution because criminals don't follow the laws. So there's P25, you can do lots of things. So another thing you can do is, if we go back to GNU Radio, we can go, or wrong folder, so we can receive FM signals. We can receive, is this the dual? No, this is not the dual. Do I have the 2 one? I'm trying to remember. Or no, I don't. Okay, so anyways, you can receive FM radio signals in GNU Radio, so I'm gonna unplug this so I don't have to do switching stuff, but so right now this would be trying to receive I think this one didn't work actually. Anyways, you can receive all sorts of signals with this, so there's other stuff you can do. Want to do questions and answers now? Yes?
Yeah, now, with your equipment that you have you done either any shortwave or CB radio work at all?
Not really. I do have a ham radio license, but
You know what QRX is?
What?
You mentioned you didn't know what the GQRX is.
It's the software. It's...
Yeah, the QRX and the software is probably because it's probably the ham code.
Oh, I do know it's German, so it could be something else, yeah. I took the ham radio test at DEF CON, so I can do more stuff, but mostly I haven't actually done anything with it because the test doesn't actually quiz you on most of what would be practical to know for ham radio. Here are some additional resources for where you can find stuff.
Let me do a follow-up question on that.
Yeah.
Back during the CB radio craze back many years ago, they dropped the requirement that in order to get a ham radio license, you had no Morse code
Yeah.
and everything else, as long as you were transmitting less than 5 watts, was it, if I remember correctly?
They're talking 2 different things. The ham code, ham and CD licenses, you used to have to be licensed for CD.
Right.
That was dropped. You used to have to know code for ham license. That was dropped.
Okay.
Yeah.
Still 2 separate.
For the technician's the lowest one, right?
No, for all of them now.
Or for ham. Yeah, for ham, like I have a technician license, so I actually haven't used it yet, but I have a license. Yeah. So here are some references. This is the SDR tutorial I talked about. Here's the radio reference. RTL SDR, it's a website about this dongle, the Realtek SDR dongle, but it has a lot of good resources there. And there's SDR.ninja. It doesn't have too much information, but it has like where you can get antennas, lots of other SDR platforms. Any other questions? So, and then this is where I got some of my photos and stuff from. So This is where I got the photo of the FM demodulator. This is actually a class on software-defined radio that some professor's doing. This is where I got the block diagram of software-defined radio. This is the radio data system thing. This is about turning the Pi into an FM transmitter, which we can do. So the Raspberry Pi, have any of you heard of this? So the Pi you can use has an FM transmitter. On GPIO line 4, you can transmit RF data if you just connect an antenna to there. It has to do with when you read memory, it leaks RF, so if you read it correctly, you can do stuff. And then this is about using the Pi as a modem too. One other thing I'd like to add is here's a good diagram of the quadrature signaling. What is it? Quadrature. So if this should load one. So for this, a lot of the stuff's done in Python. With quadrature signals, you have your Q, which is your quadrature, your I, which is in phase. And your I is the real component, Q is the imaginary component. When it's capitalized, when it's lowercase I is the imaginary constant. And the reason you use quadrature is, so right now, time is coming out at you, and you have the signal going around. So this quadrature is used for, say, FM radio. You'll see it will deviate like that. I mean, not FM, AM. So you just measure the distance from the center to here, which means you don't need to do any averaging or stuff. And then this is what's called phase shift keying, where the frequency of the signal stays the same, but it shifts the entire signal left or right. So if you look at this in the time domain on just, I think this would actually be just the real component, but this says the imaginary part. You'll see these jumps here. And then if you look at the other part, it just looks like a normal sine wave. But when you look at it from the complex view, we can say, which way is it spinning? Is it going clockwise or counterclockwise? And we can use that to determine it. So complex numbers, they look it up online. Mike Osmond's thing, again, has more information on it. I'd also like to thank these people for helping with the presentation and teaching me a lot about software-defined radio. And then I do plan on putting a lot of the stuff I used in a GitHub repository. So it'll be under me. I haven't posted it yet, but there's a lot of stuff you can do. Any other questions?
I have a question.
Yeah?
Which blade has the most sensitive input?
Oh.
Sensitive receiver, so I can pull crap out of a lot of
So both of the Blade RFs have the same thing. Where is it? So the reason I have two prices here is the Blade RF actually has a similar thing to the two USRP ones. Should have been consistent and kept the same. But anyways, this has a 40 KLE, 40,000 logic elements FPGA. This has, I believe, it's 150. So if you want to do stuff in the FPGA, you can use this.
I'm thinking signal to noise.
Oh, which of these?
Signal to noise ratio. I have a signal.
I don't know.
In something
Yeah.
like a Wi-Fi or.
Yeah, I'm trying to think. The Realtek dongle is probably not going to be what you want. USRP might be good. I know the Blade RF was designed to has more of a research grade thing, so it has like lower noise. Another thing you do is you might want to look at using external filters and amplifiers. So
I looked at your presentation when you posted. What was that info posted?
I haven't posted it yet. Oh, so I'll have a GitHub repository. It's github.com/DocProfSky. There's my email and my Twitter handle. Any other questions?
What's the legality of transmitting?
Transmitting, there are these things. Have you heard of the ISM bands? Oh, you still?
The Blade RF is capable of transmitting over a huge spectrum.
Yeah, of up to 40 megahertz. So
There's legalities in transmitting
Yes.
over parts of that spectrum.
yeah, so with the ISM bands, I looked this up online briefly. I'm not the absolute authority on this, so you find this yourself, and I'm not responsible when the FCC comes knocking on your door with the white vans filled with $3 million of equipment. But as far as legality goes, if you're in the ISM bands and you're transmitting not too high power and you aren't interfering with anything, you're probably fine. If you're using the Raspberry Pi as an FM transmitter, make sure there's nothing on that frequency where you're transmitting on before you transmit. As it is the Pi, if you look at it, you'll see a lot of harmonics, and that's because you have it's essentially using noise that they know how the noise is generated to do it.
Do you have any blades that will do agile transmission? Transmit on this band, shift, transmit, shift?
So probably the easiest way to do that would be something like the UMTRX, because the UMTRX is essentially two of these. So you could have one transmitting on one band, the other is on the other band, and you do something like that where they each swap over. Or what you might want to look at is, I'm not sure how quickly these can retune too. One other thing that is interesting is, I'm trying to remember where did I put this. There's the data sheet for the transceiver in here actually has a really nice block diagram of what SDR looks like. So this is some of the stuff I was talking about. So here are the amplifiers. This is a mixer that has a 0-degree offset, so it's like, are you familiar with phase and measuring the phase angle in degrees? Is anyone here not? Essentially you have the degrees offset, so 90 degrees is a out of phase, essentially. So if your peak's here, your next peak will be here if it's out of phase versus instead of being like that. So you have the 0-degree and 90 degrees out of phase to get the quadrature signal. Then this goes through another amplifier. So here's your initial amplifiers. Typically, the 2 here means the differential pair. Typically, these are tied together. In the blade RF, you don't need to worry about it, really. But then it goes through the mixer to shift it down and get you the I and Q. You then get more amplifiers, a low-pass filter to make sure you don't get any high-frequency additional noise added in. Another amplifier, you get these signals here, you can connect in your own IQ signal source if you want to do, if you have a different mixer or stuff. That's connected to these headers on the blade RF here. And then this goes out to the ADCs and stuff. So that's just that. There's other architectures. The PAC RF uses a few different chips instead of one integrated solution. Any other questions? Yes?
Do any of those hardwares do frequency hop, and do you know how fast it can hop?
So I don't know. I know they all can. They can retune quickly-ish. I'm not sure exactly how fast. Most of it's software again. I don't know. It also is how wide is the hopping area. This can do up to 40 megahertz. So if it's hopping within that frequency band, you don't need a hop. You just tune to the band and.
Well, the technology that I saw uses an FPGA. If you want to do frequency hop, you want to use a DSP, something a whole lot more faster, calculated.
To calculate it, but yeah, the tuner still has to be able to tune to the frequency,
you-
unless you're within the band.
Well, what you could do is you could
You
implement.
leave the tuner, so you put 2 tuners or 4 tuners, depends on how fast you want to switch.
Right.
And then interleave them where you have the tuners tuning, and you enable it to the antenna as you
Yeah.
walk around.
Or you have 2 antennas too. Another thing you could do is you could have it where the FPGA, you program it, you give it a stream of frequencies to tune to in a time order, and it will do that for you. A lot of it's how good is your programming ability. Any other questions? Yes, last question?
I had one last question. I mean, all this stuff seems really cool and interesting. It seems like you've done a lot of work on it. What do you see as a practical like job outlook, or what type of positions are available in this work area?
RF engineers will use this a lot for testing and developing new RF protocols. A big place that you'll see SDR sold is, hey, there's like open source software, here's software, hey, here's a hardware module you can buy that you can use with this software to develop new cellular stuff. That's a big one. The government uses, or you could use these, we think the government may be using these to look at emissions from the stuff to try and decode stuff from it. But there are a lot of uses. Most of it's RF engineers, but it's now becoming more of a hobbyist thing too. A lot of it's also used for radio astronomy and ham radio. The original SDRs, they used your audio jacks in your computer, but since that typically only goes up to 48 kilohertz or 96 kilohertz, or samples per second, you don't get that great of a bandwidth.
There are companies that hire.
Yeah.
Yes, guys, yeah.
Yeah.
A lot of them fundamentally works with radar processing and all sorts of stuff like that.
Yeah. Cool. Thank you.
Thank you.